So I'm Lee from ECE department, currently associate professor. So I'm very happy to introduce our Prof. Yang Wang. So Yang is actually my classmate and old friend. We attended in the early 2000 the graduate school together at the CS department. So am I still here? Somehow it's being okay.
I can hear you. Yeah.
So he was then a master student and I was a PhD student at that time. I think he then went to Simon Fraser University to pursue the PhD study, and then a postdoc at the University of Illinois. After that, he's back to Canada at University of Manitoba, and he's now associate professor at the CS department there. He's currently on leave to work in the industry. So as the chief scientist in computer vision at NOAA's ARC lab, Huawei Technologies, Canada. His research focus is on computer vision, machine learning. He received the 2017 Falconer Emerging Researcher Award in Applied Science at the University of Manitoba. He currently holds the inaugural Faculty of Science Research Chair in Fundamental Science at U Manitoba. So without further ado, so Yang, please, I think stage is yours.
Okay, great. Thanks a lot, Lee, for the great introduction. Yeah, so as Lee mentioned, so actually I spent 2 years, 2 wonderful years as a master's student at the University of Alberta. Actually, that's when I got exposed to this research area of AI, machine learning, and decided to choose this as my academic career. Okay, so yeah, so it's great to be back and visit UA, at least virtually. Okay, so today I'm going to talk about some topic I'm very excited about. I call it self-adaptive visual learning. So as Lee mentioned, so I'm actually having 2 jobs right now. So I'm a professor at Manitoba, but I'm also on leave at Huawei. So today I'm mostly wearing my professor hat. So most of the work I'm going to be presenting was done with my student at the university, but towards the end, I'm also going to present a little bit on some of the work we did at Huawei, okay? Oops. Oops, for some reason, it's not advancing, okay. All right, so as many of you know, so in the last decade, we have seen tremendous progress in the field of computer vision, machine learning, and AI in general. So for example, let's take an example of a classic computer vision task, such as image classification. So for this task, the task is you are given an image and you want to predict which objects are in the image. And for this particular task, one of the benchmark data set is called ImageNet. So on ImageNet, you are given millions of images, and the goal is to classify each of the image into one of the predefined 1000 category, okay? And this plot over here shows the error rate on this challenge over the years since it was started in 2010. So as you can see, the error rate keeps decreasing over each year. And around 2015, 2016, the computer vision system actually outperformed human performance, okay? So if you look at some other computer vision tasks, such as the object detection, so here I'm showing a result of a current state-of-art system. So you can see that even though the image is very complicated, so there are many different objects, there are heavy occlusion in the image, but the current system can pretty reliably detect all the objects or even labeling every pixel according to the object that it belongs to. So let's look at some other tasks, such as human pose estimation. So here I'm showing you the output of one of the state-of-art system called OpenPose. So you can see, though, even though this is a very complicated scene, there are multiple people and there is heavy occlusion, but the current system can pretty much reliably detect the joints of all the person in this video. So over the years, we have seen the same story over and over again. So whenever you have some kind of a computer vision or machine learning problem, as long as you can collect a very large amount of training data, to some extent that problem is almost solved, okay? Because you can just build a very big neural network to solve that problem. So given all the amazing results we have seen so far, so the next question to ask is machine learning or computer vision really a solved problem now? So where the field is moving in the next 5 to 10 years, so is there any additional technical challenge we need to overcome in order to make this technology really ubiquitous in our life? To answer that question, I want to first, let's first look at the pipeline of how we are building machine learning system nowadays. So for any computer vision or machine learning task, typically the first thing you have to do is you have to collect some training data for your task. So once you collect the data set, then building a machine learning model pretty much can follow exactly the same recipe, okay? So you take your data set, you train some model. So nowadays, typically you use some kind of a deep neural network as your model. Then finally, once the model is trained, you deploy the model to serve the end user, okay? So for example, the trained model might be deployed to run on the cloud and serve all the user requests via the web, okay? So most of the research in computer vision and machine learning has been focusing on the first two parts of this pipeline. So for example, on the data side, we have a lot of work that try to collect a different data set for different tasks. And in computer vision, the most famous data set is perhaps the ImageNet. And we also have tons of research that's trying to build more powerful models. So the general trend is that the bigger model tend to give you better performance. So in order to train those really big models, nowadays, typically we take advantage of the powerful GPU hardware. For the last part of this whole pipeline, I think we haven't really seen too much research yet. So mostly we take the deployment part of this entire pipeline for granted. So in this talk, I'm going to argue that this standard pipeline make a very important assumption, okay? So it implicitly assumes that you are going to use the same model for all users or all application scenarios, okay? So basically, it makes this kind of a one-size-fits-all assumption, okay? And this kind of this pipeline has been made popular, I believe, by those kind of large internet companies. So for example, web search is perhaps one of the early success of machine learning in large scale. And for web search, I think this pipeline makes a lot of sense because the search engine has to handle the queries that's coming from all over the world. So it's probably okay to assume that you are only going to have one single model for the search engine. And because the search engine is running on the cloud, so you can reasonably assume that you are going to have enough computing power on the cloud in order to run that model, okay? So the overall deployment of those kind of web applications tend to be reasonably simple. So in the past few years, a very clear trend in the field is that now AI and machine learning are starting to entering into many other industries beyond consumer internet. Things like healthcare, agriculture, manufacturing, retail, transportation, logistics, and so on. For a lot of those applications in those industries, quite often running the AI models directly on the cloud is not an option because of the reasons such as privacy, latency, and so on. Quite often, we have to run those AI models on so-called edge devices. And I believe in the next 5 to 10 years, a lot of the innovation of AI research is going to come from those applications enabled by edge devices. So when we build an intelligent system on the edge, we face some additional challenges. So for example, a lot of those edge devices, they tend to have all kinds of hardware limitation and privacy concerns. So although the applications on the edge device has some special property that makes it more challenging to build an AI model, as I mentioned, because of the hardware limitation, but at the same time, I'm going to argue that these applications also have some special property that could potentially make building AI model easier. And ideally, we should take advantage of these property. So in this talk, I'm going to focus on one particular property. I call it data locality, okay? So data locality just means that in a lot of those edge device applications, the system only need to deal with data that are coming from a very specific user or very specific domain, okay? So let's look at some concrete example. So imagine you have a home robot and you bought this robot and you put it in your home. So for this robot over here, it probably needs to do some computer vision tasks, such as recognizing objects, okay? Then for the AI model that are running on this particular robot, as long as you can recognize the object in your own home, you don't really care how well this robot recognizes objects in other people's home, okay? So in other words, the images that this particular robot has to handle is extremely constrained because it's only coming from one particular home. So let's look at some other examples. Suppose you have a surveillance camera. And for this surveillance camera, you probably want to deploy some model, for example, to detect people, detect the vehicle, and so on and so forth. Again, because this camera doesn't move, so it's fixed at a particular location and angle. In other words, the images that are coming from this camera is extremely constrained, okay? So as long as the for this particular camera, as long as the model can handle the image that are captured by this particular camera, it doesn't really matter how well the model handles other images that are coming from other cameras, okay? So let's look at some other example. Let's say, for example, if you have a self-driving car. Some of you may say, oh, because the car is moving around, so maybe in this application, the data is not that constrained anymore. But I'm going to argue that even for self-driving cars, in most cases, the car is only going to be driving within a very constrained environment, such as within one city, okay? So in other words, in most cases, the images that the car has to deal with only coming from a very constrained environment, okay? So if you look at some other applications like mobile devices or wearable devices or other sort of medical devices that the people wear on their body, quite often for a lot of those applications, the AI model running on those devices only have to deal with data about a particular user or a particular patient, okay? So unfortunately, nowadays, when we build AI models that are running on those edge devices, we don't really take advantage of this kind of a data locality problem. Instead, we still largely follow the same kind of a one-size-fits-all pipeline that has been made popular by web applications, okay? So now the only difference is that now instead of deploying the machine learning model to be running on the cloud, we directly put the learned model on those edge devices, okay? So in this work, in this talk, I'm going to argue that this kind of one-size-fits-all pipeline perhaps is becoming a bottleneck for building better AI models. A lot of the challenges that a lot of the AI model facing today are, I think, to some extent, are due to this fact that we are using this one-size-fits-all approach. Okay. All right. So now let's look at some of the challenges that the current AI system has. So for example, one of the challenges that I'm sure many of you probably already encountered in your own work. Okay. So this is called a domain shift. Okay. So basically, it means that because it's very difficult to collect training data for every application. So the common practice is, suppose you want to build an image recognition system. Typically, what you do is you are going to build, you are going to use some kind of off-the-shelf data set, such as ImageNet. Okay. Then once you train the model on the ImageNet, you directly deploy the model for the target application, such as the surveillance. Okay. But the issue is, the images that are coming from the ImageNet, they tend to look very different from the images captured by a surveillance camera. So if you directly use this kind of one-size-fits-all approach to train a model on ImageNet, then directly deploy it on surveillance, quite often you are going to see a significant drop in performance. Some of you may say, oh, I know how to solve that domain shift problem. This is because my training data is not diverse enough. Then maybe what I can do is just to collect more training data, okay? But I'm going to argue that just collecting more data is not going to completely solve this domain shift problem. So the reason is because our visual world naturally have this kind of a long tail distribution. So regardless how big the data set is, quite often you are always going to have some phenomena that somehow dominate the data set, where there are some other rare phenomena where you don't have enough training data. So there is always this kind of a tail in your data set where the performance of the model is going to suffer. Okay. So this kind of a long tail nature also can lead to some very negative consequences. So many of you have heard in the news that the AI model tend to amplify the bias in the training data. So for example, if you train a face recognition system on a data set that consists of mostly predominantly males, then the model is probably not going to work well on images of different gender or different skin colors. So another issue is that even if you can collect a big training data, you can train a big model. But the issue is that those edge devices, they tend to have very limited computing and memory. So if you have a big model, quite often it's often a challenge on how to actually put the model in the edge device. Okay. All right. So in this talk, I'm going to try to advocate a slightly different way of thinking about building machine learning and computer vision pipelines. Okay. So during the offline training stage, we are still going to have, just like a traditional machine learning, we are still going to have some data set and we are going to train some kind of a generic model. But the difference here is that now instead of directly deploying the same model to every user, what we are going to do is that based on some information about every specific user, we are going to make some adaptation to this generic model so that the adapted model fits this particular user better. Okay. So here I'm drawing the icon of different user, but you can easily imagine this could be different application scenario or different domain and so on. So for training this generic model, so typically it can be done on the cloud or maybe on some kind of a powerful GPU server. And for this adaptation, usually it's done on every user's edge device. Okay. So I think the advantage of this new pipeline is that because now for every user, it has its own adapted model. So almost by definition, we alleviate some of the issue of the domain shift. Okay. And also because the model deployed for a particular user only need to handle the data for that specific user. In other words, the data this adapted model has to handle is very constrained. So we may have a better chance of somehow compressed model have to have a smaller size. Okay. All right. So in the rest of the talk, I'm going to present several pieces of work that we have done in the past 1 or 2 years, where we use this kind of a self-adaptive idea for different applications. So because I'm a computer vision person, most of the application I'm considering are computer vision, but hopefully if you are not working on computer vision, hopefully some of the idea can also be used in other applications as well. Okay. So let's start with the first work. I call it scene adaptation using meta learning. So here I'm going to use crowd counting as a running example. So for crowd counting, the problem is you are given an image and you want to count how many people are there in the image. Okay. And the common way of solving the crowd counting problem is you first, given an image, you first try to estimate something called the density map of the input image. So every pixel in the density map is a number representing the level of density at the corresponding location in the image. Then once you have the density map, you just need to sum over all the value in this density map. This will give you the total number of people in the image. Okay. So basically, the key of building a crowd counting system is how to estimate this density map. So traditionally, a lot of the work use fully supervised approach for density estimation. So the idea is you just collect a training data set where you have this kind of input image and the ground truth density map. Then you just build a neural network to estimate the density map. Okay. But the key question is, for this crowd counting application, how we are going to collect our training data. Okay. So one way of collecting training data is you could just collect all the images from the same camera scene. So in fact, some of the benchmark data set in the literature are collected this way. But the problem is if you collect data set this way, the model you train it probably is going to overfit to this particular camera scene. Okay. So if you try to deploy the model in a different camera scene, the performance is probably not going to be so good. Okay. So a better way perhaps is we can build the data set by collecting images from many different camera scenes. Okay. And because now the image is coming from many camera scenes, hopefully the model is not going to overfit to a particular camera scene. But the issue of this approach is that it doesn't really take advantage of the data locality property in deployment. Okay, because for crowd counting application, during testing, we know that all the test images are going to be coming from the same camera. Okay, so then it doesn't really make sense to learn a very generic model. So instead of what we want to do is we want to get a model that are somehow specifically tuned to a particular camera. All right, so then in this work, we propose this problem called scene adaptive crowd counting. So our assumption is during deployment, we can during deployment, we have a new target camera, and we are going to assume that we can obtain a small number of labeled images from the target camera. Okay, then our goal is to quickly adapt the learned generic model to this target camera so that it fits this target camera better. All right, so now let's look at the problem setup in a little bit more detail. So we have this kind of an offline training stage. During the training stage, this is what our training data look like. So our training data is going to consist of images collected from many different camera scenes. And for each of the camera scene, we have a collection of images and their ground truth density map. From those kind of images, what we want to do is we want to learn some kind of generic model with parameter theta. Then during deployment, we have a new camera scene that's not a part of the training scenes. Then for that new camera scene, we assume that you have a small amount of label data. Then based on those small amounts of label data, we want to adapt the generic parameter theta to become theta tilde, so that the theta tilde is specifically tuned to this target camera. Okay. So the key thing is that the number of images that we have during deployment has to be very small, because during deployment, usually you are not going to be the user is not going to give you hundreds of millions of images. So quite often they can only collect maybe 1 to 5 images. Okay. So then the key question is how we learn this parameter theta in such a way that it's ready to adapt to a new camera scene with only small amount of label data. So here for this application, we have camera scene here, but you can imagine that the same idea could be used to adapt to different user or different domain and so on. Okay. All right. So the technique that we are going to use is based on something called meta learning. So basically, let me just give you a very high level overview of meta learning. Okay. So the original purpose in the original work, the meta learning is proposed to solve this kind of a few shot classification problem. And the way that the meta learning works is that it has this kind of offline training state. In meta learning, it's called a meta training. Then during meta training, what you do is you construct a lot of few shot image classification tasks. Okay. So by learning from the task, then basically the learned model can learn to better sort of adapt to a new few shot classification task. Okay. Then during the testing, or in meta learning terminology, it's called meta testing. You are presented with a different few shot classification task. Then the model is going to be able to quickly adapt to this new task. Okay. All right. So now let's look at how we set up our problem using the meta learning setup. Okay. So remember, in meta learning, we have the meta training stage and we have the meta testing stage. So during the meta training stage, so this is how we organize our training data. So basically, remember I mentioned earlier, during the offline training, we have training images that are collected from different camera scenes. So each of the tau here corresponding to a camera scene during training. Okay. So for each of the training scene, we are going to split its data into its own training data and its own test data. So for example, tau1 here means the first training scene, then it has its own training set and its own test set for tau1. Okay. Similarly, we do the same thing for other training scenes as well. So during meta testing, what we have is we have a new camera scene, and for the new camera scene, we have a small amount of training data. Those are labeled. Then what we want to do is we want to use those small amounts of training data to adapt the model to the new camera scene. Then we evaluate how well the adapted model is doing on some test data that are coming from this new scene. Okay. So the key thing to remember here is that the number of training, the size of the training data in all the training scene has to be very small. Because remember, our goal using meta learning is to simulate what's going to happen during testing. Okay. Because during testing, we know that we are only going to be given a very small amount of label data for the target scene, so that during the meta training stage, we need to simulate this kind of few shot learning environment. Okay. All right, so this is what the algorithm looks like. So let's start with some global parameters data. Then during one iteration of the algorithm, what we are going to do is we are going to sample several training scenes. Okay, so each of the tau here is a sampled training scene. Then for each of the sampled training scene, what we are going to do is we are going to do a little bit of adaptation so that we change from the global parameter theta to to the adapted model corresponding to each of the sampled scene. So for tau1 here, then we change this global parameter theta into theta1 tilde. Then theta1 tilde is going to be a model specifically tuned for the first training scene. And similar, we do it for other sampled training scenes. Okay. Then what we do is we are going to evaluate how well the adapted model is. Okay. So for example, for this adapted model for tau1, we are going to evaluate how well this adapted model is using the test data corresponding to that training scene. Okay. So remember, I mentioned earlier, for every training scene, you have its own training data and its own test data. So we use the training data for this training scene to do the model adaptation. Then we use the test data of this training scene to evaluate how well the adapted model is doing. Okay. All right. So then what we are going to do is we are going to accumulate the information of how, we are going to accumulate the loss across all the sampled training scene. Then this is going to give us a final loss in the end. Then we just use that loss to do a update on the global model. Then you just repeat this process. Okay. So basically, this kind of a adaptation from the generic model to scene-specific model is going to be the inner loop of our algorithm. And this update of the global parameter theta is going to be the outer loop of the algorithm. Okay. All right. So let's look at some of the detail of the algorithm. So remember, in the inner loop, what we want to do is we want to adapt the generic model theta to a scene-specific model theta I tilde. Okay, so imagine now we are doing the adaptation on the ice training scene. Okay, and the way we do that is we just take a few gradient updates based on the loss that are calculated on the training data of this scene. Okay, so remember I mentioned earlier, for every training scene, it has its own training data. Okay, then what we do is we calculate the loss on the training data of this training scene. Then we take a few gradient updates. So that's how we get the adapted model parameter. So then what we are going to do is we are going to evaluate how well the adapted parameter is doing in this particular scene. Okay, and the way we do that is we just calculate the performance on the test data of this particular training scene. Okay, so remember, every training scene has its own training data and its own test data. So in order to evaluate how well the adapted model is doing, we just calculate some loss using the test data of this training scene. Okay, so that's the inner loop of the algorithm. Then for the outer loop, what we do is we just accumulate the loss calculated across all the sampled scene in this iteration. Then we sum the value together. Then we just take the gradient update on the global model. Okay. So basically, the high-level intuition is that we are learning this global model to have the property that given a new target scene and given a small amount of label data from the target scene, is going to be able to effectively adapt to that target scene. Okay. All right, so let's look at some quantitative results. Here we are. I'm showing you the error on one of the benchmark data set. So lower means better. So you can see that our approach outperforms other alternatives that are not doing this kind of a scene adaptation. Okay. All right, so that's the end of the crowd counting. Then we also use exactly the same idea for some other computer vision tasks. So for example, we use it for anomaly detection. So for anomaly detection, the problem is you are given some training videos, and in the training video, you only have normal behavior. Okay. Then what you want to do is during testing, you might encounter some anomaly that you never encountered before. So the goal is to identify those frames that has anomalies. Okay. So the traditional way of solving the anomaly detection problem is you just train a single model using the whatever training data you have. Okay. But the issue is that model you end up with is going to be too generic. Okay. So remember, for those kind of anomaly detection application, typically you have some kind of a surveillance camera that doesn't move. Okay. So in that case, it doesn't really make sense to have some kind of generic model. Instead, you probably want a model that are specifically tuned to the target surveillance camera. Okay. So now in this work, we use exactly the same idea. So during training, we learn from a collection of many different videos captured by different camera. Then we learn some kind of generic model. Then during testing, we have a new video. and we observe the first few frames of the video, and the model is going to adapt itself according to the first few frames. Then it's going to do the anomaly detection on the remaining frame of this this target video. Okay. All right, so without getting too much into the technical detail, let me just show you some of the results. So here I'm showing accuracy, so higher means better. So you can see that our approach performs significantly better than other alternatives that are not doing this kind of scene adaptation. Okay, so I'm particularly excited about the last result, because this UR4 dataset is actually not an even RGB video. So in this dataset, it consists of videos that are captured by a depth camera. So even though during training, all of our video are RGB videos, but during adaptation, we can actually adapt to a different sensor modality. All right, so that's the first piece of work on using on scene adaptation using meta learning. So now I'm going to move on to the second approach, where we do adaptation using something called the HyperNet. Okay. So the motivation of this work is that after we did that crowd counting work I showed earlier, we're not completely satisfied. Okay. So the reason is because that meta learning approach still requires that during deployment, you need to have a very small amount of label data. Okay. But in reality, quite often asking the user to label images is very expensive. So usually users don't want to label anything. Okay. So then the question we want to ask ourselves is it possible to do the adaptation without requiring any label data? So instead, can we just do the adaptation using only unlabeled data captured by the user? Okay, because asking the end user to just take a few pictures is very easy. It doesn't really cost too much, but asking them to label the image is much more expensive. Okay. All right, so then in this work, so then basically motivated by this, we have a new setup for the problem. So during offline training, the setup is exactly like before. So we have training data that are collected from many different camera scenes. Those are all labeled. Okay. Then during the difference is during adaptation, we no longer require label data from the target scene. Instead, we only require a small amount of unlabeled images. Okay. So from the unlabeled images captured by from the target scene, we want to adapt our model so that the model becomes better suited for the target scene. Okay. All right, so we call our model AdaCrowd. So this is what the model looks like. Okay. So the first row here is just a standard crowd counting neural network. So basically, this neural network is going to take the image as input and produce the density map as output. But the special thing is that in this neural network over here, we insert some special layer, which we call the guided batch normalization layer. Okay, and this GBN layer is going to have some learnable parameter inside of those layers. But instead of learning the parameter of those GBN layer together with the rest of the neural crowd counting network, what we are going to do is we are going to have a second neural network here. We call it the guiding network. The guiding network is going to directly produce the parameter in those GBN layers here. Okay. So basically, what the guiding network is going to do is it's going to take an image from a particular scene as the input, then directly output the parameter in the GBN layer for this crowd counting network. Okay. So this is in deep learning, sometimes this is called a hypernetwork. So this is a little bit different from the standard way of using neural network. Because in standard neural network, typically the output is some kind of a label, but here the output of the guiding network is not any label. Instead, it's the parameter of another neural network. Okay, and because the input to the guiding network is going to be slightly different for different camera scenes, which means the parameter in the GBN layer is also going to be different for different camera scenes. So that means the crowd counting network in the end is going to adapt itself to different camera scenes. Okay. So one thing to notice is that in this whole network over here, we only need the supervision at the very end. Okay. So in other words, this guiding network doesn't really require any label data. So the supervision only comes from the very end, and the gradient is going to back propagate through the crowd counting network and through the guiding network. Okay. All right, so now let's look at some of the experiment results here. Again, I'm showing the arrow here, so you can see that our approach out of other alternatives that are not doing those kind of scene adaptation. Okay. All right, so then we use exactly the same idea for a slightly different computer vision problem called highlight detection. Okay, so in highlight detection, the problem setup is you are given a long video and you try to identify something called the highlight or moments from the video. So for example, the input could be an hour-long soccer game, and the moments of the video could correspond to those small clips that maybe some player got a point or something like that. Okay. So in the literature, most of the work in highlight detection assume that you have training data, you just learn a generic highlight detection model, and all the user is going to use the same model for highlight detection. But the problem is that different users, quite often, they have different opinion on what they consider to be interesting, okay? So then in this work, what we want to do is instead of having a generic model, what we want to do is we want to build a personalized highlight detection model for every user so that we can do some kind of a personalized highlight detection. All right, so basically in this work, our assumption is that for every user, we know something about the user history, okay? And in particular, in this particular work, we assume that the user history consists of the highlight that a particular user has created before, okay? And our assumption is that the highlight that this user has created before tell us some information about what kind of information this particular user is interested in, okay? So then based on the user history, what we want to do is we want to build a personalized highlight detection model so that it can produce output that are specifically tailored to that particular user, okay? All right, so this is what our model looks like. So you can see that it's almost identical to the unlabeled scene adaptation in crowd counting I showed earlier, okay? So the first row here is just the standard highlight detection model, which takes the raw input video and produce the highlight as the output. Then in this network, you have some layer with some learnable parameter. Then you have another neural network. Here we call it the history encoder network, where this network over here is going to take the user history as the input and directly produce the parameter in this red box over here in the highlight detection network. Okay, so through this history encoder network, we can allow the highlight detection model to adapt to different users based on their preference. Okay. All right, so here I'm showing you some quantitative results. So you can see that again that our approach outperform other alternatives that are not doing this kind of user adaptation. Okay. All right, so finally, I want to show another recent work we did at Huawei, where we use something called the test time adaptation using meta-auxiliary learning. Okay, and for this work, we are going to look at the application of dynamic scene deblur. So the idea is you are given an image with, you are given a blurry image. So the blur could be caused by many different factors. Could be like, for example, camera motion, or maybe there is the background is moving, the object is moving, and so on and so forth. But for whatever reason it is, the input is the blurry image. Okay. Then what we want to do is we want to do a deblur on the input. Okay. So we want to produce this kind of a clean image as the output. So in the literature, a lot of the recent work on this area use deep learning approach. So the idea is you just collect a training data consists of input image, which are blurry image, and the corresponding output, which is the clean image. Then you just throw that training data into a deep neural network, and the network is going to learn how to do the deblur. But this kind of approach ignores the fact that for different input image, quite often they have different statistics. Okay, so in this work, what we want to do is, can we somehow adapt the model a little bit for every test image? Okay, so that's a high level idea. All right, so basically, then in this work, we propose something called the test time adaptation using algorithmic task. Okay, so the idea is we are going to have a neural network that's performing the so-called primary task. In our case, the primary task is just the deblur task. Okay, Then what we are going to do is we are going to attach another so-called auxiliary task to the network, okay? So the key thing is that this auxiliary task has to be something called self-supervised. In other words, this task has to be something that does not require actual labeling, okay? So suppose you can construct this kind of architecture. Then during testing, what you can do is you can actually update the model parameter using the loss defined on the auxiliary task. So remember, auxiliary task is something that does not require labels, which means you can define this task, you can define the loss on this task based on just the input itself. Then what's going to happen is the parameter in this network is going to change, okay? Then what we are going to do is we are going to use the updated parameter to perform the primary task for this particular test image, okay? All right, so this is so in this work, what we did is we use the image reconstruction as our self-supervised auxiliary task. Okay, so this is what our architecture looks like. So we have a network which is a shared backbone. Then from the backbone, we have two branches over here. So the first branch is going to perform the image deblur. Then the second branch is going to perform the image blurry image reconstruction. Okay, so now the question is, how do we learn the parameter in the model so that we can perform better for the deblur task, okay? So for the learning, we use something called meta auxiliary learning. So the idea is, suppose these are the training images you have. For a particular iteration of the training image, what we are going to do for the training, what we are going to do is we randomly sample one training pair. Then for what we are going to do is, remember this parameter theta here is our generic model. What we are going to do is, given this input over here, we are going to do a little bit of adaptation of the model so that we get a sort of adapted model for this test image. And the way we do the adaptation is just by taking a few gradient updates using the loss defined on the auxiliary task. Okay, so through this auxiliary task, we get a updated model for this test image. Then what we are going to do is we are going to use the updated model to perform the primary task, which is image deblur. Okay, so this is going to be the output of the deblur network in the end. So remember, here we are talking about the training. Okay, so which means for this input over here, we also know the ground truth. That means we can define a loss of how well the primary network is doing by just comparing the prediction of the deblur network with the ground truth. Then this is going to give us loss that we can use to update the global parameter theta. Okay, now we just repeat this process many iterations until it converge. Okay, so the high level idea is now we are learning this kind of a primary task and the auxiliary task in such a way that the auxiliary task during testing is going to help us to adapt the model to perform better for the primary task. Okay. All right, so without getting too much into the detail, let's look at some results. You can see that our approach outperforms other alternatives as well. So here are some more qualitative example, we got during testing. Okay. All right, so I'm almost done. So basically, in this talk, I have shown several pieces of work towards this general goal of building computer vision systems that adapt to every user or application scenario. So we look at three different kind of approach for this kind of adaptation using meta learning, HyperNet-based, and meta auxiliary learning. Okay. So I think there are a lot of interesting follow-up work in the future. So for example, right now we assume that this adaptation is only done once during deployment. But you can imagine that how to do this kind of adaptation continuously while the user is interacting with the model is going to be an interesting topic. So another interesting topic is, so far we have to assume that during meta training, we still need to put all the data in one central location. So can we somehow do the meta learning in a federated way without collecting all the user data in one central location? I think that's going to be a challenge. So far, we have only been talking about adapting model parameter, but you can imagine that in the future, suppose we can also adapt the model structure as well. So in addition to updating the parameter, we also make the model smaller. So I think that's going to be a very exciting future work. And this, finally, I think somehow combining this kind of a model adaptation with more sort of like a reinforcement learning kind of idea to basically like imagine you have a robot the robot can decide by itself where to collect those kind of data that are later being used for adaptation. I think that's going to be a really interesting research question. And also, I think there are a lot of application areas that could potentially benefit from those kind of ideas, and I'm interested in explore those applications as well. So finally, I want to acknowledge all my students at Manitoba, also some of my collaborators at Huawei that contributed to the work that I presented. That's all for me, and I'm happy to take any questions you have. Thank you.
Yeah, how are we taking the questions, Lee? Otherwise, I have a question already. I have actually 3 questions. Can I start? I can break the ice, and then others will follow. Actually, I have 3 questions. I really like this idea of adaptation. And while you implemented them in computer vision, actually it can be applied in many other contexts. So the first question that I had, you addressed it in your first, you mentioned it in your future work. I was wondering about continuous adaptation, but you mentioned continuous adaptation when you have a change in the environment, but it can be continuous adaptation also even if you don't have a change in the environment, because the adaptation is done with very small data set, but as you're after deployment, you keep getting data and you can continuously adapt. So is that a possibility? That's my first question. My second question has to do with, you mentioned adaptation based on this, well, one of the properties you were talking about, computation at the edge. So if I'm deploying my model, let's say in a wireless sensor network, and your module has other constraints like computational constraints and energy, can you adapt to the availability of energy? So it's not running on the server that has infinite energy, but it's running on a sensor. You don't have energy. So can you adapt your model to be able to run with lower energy? And then finally, the other question has to do with explainable AI. So imagine you build a big model and it's running on your server. It's very generic, so it recognizes all these animals or whatever. And you can build what some people call explainable AI in that case, if you use attention mechanism to put a heat map on the image to tell you where my model is focusing. So now you adapt your model to a particular camera, let's say. Will that explanation follow? Or do you need also adaptation of the explanation?
Okay, great. Those are really great questions. By the way, for those who don't know, Osma is actually my master's supervisor. Okay.
Years ago.
So let me answer those questions one by one. So the first question is about continuous adaptation, even in the case of static environment. You are absolutely sure, absolutely right. So you can definitely do that. But I think the value of adaptation in that case might be diminishing. Because if you have a user where it has tons of data specific to that user, you might as well just build a model using the data as well. So that in the limit, I think it's going to become building a user specific model. Okay, I think the value of continuous adaptation lies in the fact that the environment is changing, or maybe the user preference is changing. Okay, so that's the first question. So the second question is about the adaptation in basically taking advantage of the sort of energy consideration. So we haven't done that. So in fact, we haven't even done the taking advantage of the model size yet. But I think the model size, in some sense, is correlated with energy, because smaller models tend to have low requirement on the energy. So that's why I think basically adapting while compressing, that's going to be a very interesting and important research direction. So the last question is about the explainability. My answer is it doesn't increase or decrease whatever explainability you already have on the generative model. So you can still do the heat map on the adaptive model. So I don't think the adaptation is going to have any either positive or negative effect on the explainability. Yeah, so that's my feeling. Yeah.
Okay.
Thanks. Any further questions, comments?
Anyone thinks of any questions they have later, like I mentioned at the start of the meeting, Dr. Wang has a bit of time this afternoon that he's willing to meet with people. So just send me an email. I'll pop my email in the chat window there, and reach out to me and try to set something up. But if there's no other questions, I think we can end the seminar a few minutes early. Thank you very much.
I have another question.
Oh, okay, go ahead, Osmar.
So one of the applications that you mentioned that I really like is I don't know how you call it, but you gave a summary of a video, like for example the scenes that are relevant, and you mentioned the fact that they're very subjective because people may be interested in different scenes. So you even mentioned the term personalization. It's not just adaptation, you personalize it to the individuals. And that gave me another idea. So if you have, and it applies to other kinds of adaptations for counting people or whatever. So you build this big model and then you adapt it to different circumstances. If you collect those models that have been adapted to different circumstances and you merge them into yet another model, will it be better than the original big model or not? So are you actually locally improving it? And if you can merge them all together, you can get a bigger and better model. Is that possible?
Yeah, I think you are way ahead of me. So, yeah, so I think yeah, definitely. If like I think if this kind of a adaptive model becomes the mainstream, the next research question is exactly what they are talking about. Basically, like because in a lot of application, like for the local user, like they do a little bit adaptation. It's okay to upload the model to the cloud, but it's actually not okay to upload their data. So then in the end, I think, but of course that's not a research question right now, but in the future, one research question we have to answer is, suppose on the cloud you have many small user model, how do you adapt, like basically combine them together? I think that's, you are absolutely right. So in the next few years, that will, I think, will become an important research question.
Cool, no, thank you.
Yeah, no problem.
Are there any other questions? No? Okay then. Well, so I think we'll wrap up. So thank you again, Dr. Wang, for presenting today.
Thank you for having me.
And we will, yeah.
Okay, thank you.
And we will see everybody next Friday for our next AI seminar. So hope you all have a great weekend.
Okay, thank you. Bye.
Oh, thank you. That was an awesome presentation. Thank you.
Thank you. Thanks for the great question.
No, thank you.
Thanks.
Thank you.